Welcome to the Big Picture Podcast. We are here with an engineer from the fossil fuel industry. His name is Rick, and he focuses on creating petroleum products from petroleum. How does it get from the ground to your gas tank? You can't just take what comes from the ground and into your gas tank. Rick, thank you so much for joining us here at the Big Picture Podcast.
Oh, it's my pleasure, John. Thank you.
How long have you been working in this industry?
More than 35 years.
And how did you get into it?
I was a chemical engineering student, and it was the highest paying job. Sadly.
No, seriously, because when you're going into college, your thinking was like, okay, what am I going to do for a career?
Oh, I wasn't thinking that when I was going into college.
Oh.
I was like, well, what am I going to study? It's like, well, I like chemistry. I really like math, and I'm good at it.
Uh-huh.
It's like, and I want to make money and engineering. Okay, I think I'll put those together. Oh, chemical engineering. And I had no idea what chemical engineers did.
Huh.
I remember when I first started studying, somebody said they were glorified plumbers. That's it. Chemical engineers are glorified plumbers.
Was that within the first year, second year, third year, not until your junior year, things started to come together that you wanted to do chemical engineering?
No. When I first went to school, because I knew out of high school, I liked sciences.
Oh. Uh-huh.
I liked chemistry. I liked math and physics.
So once you enrolled,
I was already enrolled in chemical
University
engineering.
of Cincinnati.
Yes.
Yeah.
It's a
4-year program.
5-year with a co-op. So it's the same amount of school as if you went a regular 4-year program, but it's extended because we would go 2 quarters a year working in the industry.
Oh, spread out through the program.
Yes. So you only went to school the first full year. Full year was no co-oping, and after that you worked every other.
So you're
quarter.
taking basic science courses and engineering courses initially, and then
going to work in the field. And so you actually get a feel for, is this what chemical engineers do?
Or is this what I want to do?
And then you can decide, no, that's not what I want to do, or yes, it is what I want to do.
So to get a degree in chemical engineering pretty much means you have a job waiting for you at the other end. Is that still the case today? Or how competitive is it?
I think so. I really haven't kept up on it, but I'm pretty sure they're still in demand. Mm-hmm. Back when I was graduating, the oil industry was especially hunting for chemical engineers. Nowadays, I suspect but of course, chemical companies, just about every company needed chemical engineers in some capacity. Yeah. But I suspect that's still the case, but I really haven't kept up on how the chemical engineering recruiting scene has changed.
So glorified plumbing.
Yeah, like pipes. That's what you think of when you think of plumbing, right?
Well,
I got a hot water heater. I got to plumb up a piece of pipe up to my sink.
You'll drive past occasionally a processing plant, a refining plant. Right. And if it's in the evening, you'll see it lit up.
Towers, right?
All these towers.
Skinny things sticking up into the air. And if you look closely, it's hard to see at night, you'll see a lot of pipes.
So you're telling us that you know what those pipes do? Pretty
much can figure it out. Yep.
Yeah.
I can look at a refinery from a distance, and at least I'll know some of the major, from the line size, how big is the pipe and where it's going and what other equipment is around it. Mm-hmm. At least I know. If I don't know what particular pipes are, I know what pipes they need to have, right? And it's any glorified plumber would know. I need to have pipes bringing the water to the hot water heater, and I need to have the pipes bringing the hot water and the cold water to the sink and the shower. And it's in refining, you've got certain pieces of equipment.
It's just not water.
It's just not water. That's right. Although there are pipes for water, for cooling water, for example, but you'll have pipes for the crude oil, and I need to bring that crude oil in, and I need to do a little desalting because it's pretty salty. But in any case, heat it, put it in a heater, like a hot water heater, but it's a crude oil heater, and then put it in your big tower where fractional distillation.
Hey, Rick, can you walk us through step by step the process of oil refining?
Yes, I will
Cool.
give that a try.
Thanks.
I'll keep it, of course, try to keep it brief. So we bring the crude oil in, and it often comes in by ship or rail nowadays from a lot of fracking type of operations. There's a lot of rail car crude bringing in or pipeline, but it goes into crude oil tanks. The crude oil tanks usually have water in them, so you kind of skim the water off the bottom, and then you pump the oil. So now
the water's off the
crude,
more dense.
Yes, water's more dense than crude, so it sinks to the bottom of the tank, and so you always kind of have a dewatering operation at the tank. But then you purposely, once you've pumped it into the first unit, which is generically called a crude unit, you put water with the crude oil and you mix it up real good. And what you're trying to do is get salt that is inside, mixed up with the crude oil. There's salts.
Sodium chloride, potassium chloride,
exactly.
Minerals.
Yes, minerals.
Water-soluble.
Water-soluble. And so you just mix this water up real good with the oil, and the salts go in with the water, and then you put them into big vessels with electrostatic grids to kind of help precipitate or coalesce the water droplets out. And you give the big vessels because you want the crude oil and the water to go slow, so you have a chance for the water to kind of fall to the bottom of the big vessel and the oil to go out the top of the big vessel at the far end of the vessel. And you've got these electrostatic grids in between.
There's a flow.
Yes,
within
a
this vessel.
slow flow in this vessel.
Where it enters in,
as a mix.
It's mixed, and by the time it gets to the other side, where it's separated out based upon differences in physical properties into a water layer and a hydrocarbon layer.
Exactly, yes.
Okay. A water and salt layer?
Yes, the salt is with the water.
Right.
Yep, so the water is now
Salt
quite salty, and we actually measure, by material balance. We know how much oil we put in, how much water we put in, and we measure how much salt's in the water coming out. That operation, by the way, is called desalting. I have been involved in desalting pretty closely in the past, but it's been a number of years. But I want to say it's pretty darn salty. It's percent levels.
It's up there.
It's up there. And one of the biggest problems here is not so much how much salt we're pulling out, it's how much we can't get out. And
Yeah, what's the issue with salt in the...
That is a very good question. The issue is when you later on, let's follow the crude oil on it down line. So now it's still got some salt in it, but it's going on down line, and it goes through, it gets heated now. We did some heating before, I should say, before the desalter, because when you heat oil to in the 300 degree range, of course, desalting in this large vessel we talked about and the property differences you mentioned, density is the biggest, most important one. And if you heat oil and water, the density of oil
goes down
a lot quicker than water.
Oh.
So you'll get better separation, and also the viscosity is less. So viscosity has to do with how easy the oil and the water kind of can get away from each other. And the thinner it is, if you will, the
easier to separate.
The easier it is to separate. So you heat it up, and now you've got lighter oil. And the water's lighter too, but not that much lighter, so it drops out quicker. But once you've come out of the desalter, now we really get serious and we heat it up much hotter in heat exchangers. And what we do in these, what they're called heat exchangers, is we take the hot products that we'll get to here shortly, and they're about ready to go outside the crude unit as products that go to other units, and we need to cool them down. We need to take the heat out of them. But we just don't want to waste that heat to the air, so we put it in an exchanger where the crude oil's on one side of a tube and this hot product's on another side.
You're heating the new
feed with the products that got made from the crude that came in 10 minutes ago.
So as an engineer, your prime objective is to optimize that efficiency.
Yes, that would be one of those things. And the crude, those exchangers get dirty, and but let's just say they're clean. In any case, you do all that heating, and you still have to go to a furnace. So you go to a furnace, and the crude oil's inside the tubes, and you're firing fuel, and it's just like a lot of burners, and it's a big flames, and it takes a lot of energy. So if you want to be efficient, you want to maximize how much heat you get from the products, so you don't have to burn so much fuel in the furnace. So now those heat exchangers upstream help you save fuel. But if they get dirty, If those exchangers get dirty, which they will get dirty,
they're less efficient.
They're less efficient, and you have to burn more fuel. And so, yeah, part of the job of an engineer would be to monitor the exchangers' efficiencies and know that as they're getting dirty, there is a time when I will need to take it offline and clean it. And during that time, I get zero efficiency out of the exchanger.
Do you have like two running in parallel, so something's always happening, or is it?
Yeah, it's a series of exchangers, and I may have two. But the bottom line is taking an exchanger offline isn't free. You lose energy efficiency when you first take it off to clean it, but by cleaning it, you gain more in the coming months.
So you gotta optimize when you're going to. You want to schedule when you're going to take it offline.
Exactly. Or another thing to consider, which is interesting, I always thought, was how quick does it foul up again? So you could say, oh, I'm going to clean that exchanger every 6 months. But if it fouls up in the first week after you put it online, it actually would have been better just not to clean it.
Okay, can you talk about the fractional distillation?
Absolutely. And I should have probably said that's really all a crude unit really is doing, is you take, although as we know from previous few minutes, there's a lot of other things going on. The primary is fractional distillation. So you heat the crude oil up. It's a lot of different molecules of different sizes, and you put it into what's called a crude distillation tower. And the light products boil up the tower, and the heaviest stuff falls down to the bottom, and that's the fractional distillation tower, and those are the towers you see. Usually one of the biggest towers you'll see in a refinery is the crude distillation tower.
The crude distillation tower. So the crude has been desalted, and then it goes to this biggest tower. The small molecules will rise to the top. The heavier molecules won't rise so high, and you must have like pipes coming out various heights.
Side draws is what we call them.
Side draws?
They're called side draws. And
that pull
there's certain
out.
trays. There's a series of trays inside the tower. Those are the fractional distillation trays. Mm-hmm. And then there'll be certain trays with designs to capture the liquid falling down, because there's vapor going up, liquid falling down the tower.
So the methane will stay as a gas.
Yeah, that just stays all the way up. And gasoline pretty much goes all the way up.
What's gasoline?
Like C8, C7, hexane, heptane, octane.
What proportion of that crude oil is gasoline?
Well, it depends on the crude, but
about half.
You can probably get gasoline. It's probably not half, although there probably are crudes with close to that, but I think normally more like a quarter.
So you're saying it'll depend upon where it's from? Very
much depends on the crude, and but yeah, it could be a substantial portion.
What are the differences from crude coming from different areas of the planet?
Well, there are some crudes like Arabian Light was a big popular crude, right? You've all heard about the Arabian oil fields, and
it almost sounds like you're talking about like wine.
Arabian Light,
like
yes,
beer.
That's right, Arabian Light. And then there's Canadian Heavy.
Seriously?
That's a very stout beer.
Yeah.
Yes, no, that is Canadian Heavy is a crude, and it's a generic name, but
is it from like the tar sands?
It would be like from the tar sands. So they take the tar sands and get the tar out of them and have it turn into a crude that they can pump down the pipelines.
So they're treating it to create a crude that they then send to a refinery.
There are sometimes some of the Canadian fuels are too heavy to just put in a pipeline, and so they have to do something to treat them, partially crack them if they will, make it less viscous, or put light carrier, something to thin the crude oil so it'll flow down the pipeline. And that's like the opposite end of the spectrum from something like Arabian Light, which in the old days, Arabian Light was plentiful, crude refineries take it.
Heyday.
Easy refining.
So what do they mean by a sweet crude versus a sour crude?
That is about the sulfur that's in it. So if it's sweet, it's very low sulfur. And sulfur cannot be in the product, the final product. The sulfur, obviously there's some sulfur. You can't get it all out. But generally, the sulfur levels of products is closely regulated, because if you burn a fuel with sulfur, some of that fuel, the sulfur, turns into sulfur dioxide. Mm-hmm. It is a acid rain causing molecule. So some years ago, sulfur became regulated, and it's been tightening up for decades and decades. So meaning, less and less sulfur can be in the fuels, the final product in the fuels. But the Arabian Light or sweet crude is
sweet means it doesn't have so much sulfur content.
Right. So it's easier for a refinery to take a crude oil and turn it into a product.
To what extent do the regulations of the amount of sulfur you can have in your end product impact the decisions for treating the crude? For example, if there were no regulations on sulfur emissions, would that be less of a concern to remove sulfur? Is it something the industry sees that important to do, or how vital is it that there be the governmental regulations?
Well, I'm not sure. I don't know that any refiner would to get the sulfur out of the fuel. We need other processes, and the crude unit just does the first distillation, but it has all the sulfur still in the gasoline.
So
all in the
before
diesel.
Or after distillation.
When you distill out these products, you have a pipe carrying diesel out of the unit, and you sample it, and if you were to test the sulfur content, it'd be horrible. It's full of sulfur, and that's even if it were sweet Arabian Light. There's probably more sulfur in that than you can put on the market today. So for a refiner to get that to market, they need to do additional treating.
So it's really the first step is getting rid of the salt.
The salt was just
not the sulfur.
Yeah, we never got to why you want to get rid of the salt, but it has to do with corrosion in the top of the tower.
That's not good.
You actually get hydrolysis of the salt, and you end up with hydrochloric acid gas flowing up the tower harmlessly as a gas. Mm-hmm. But then once it gets in the overhead and you start cooling, you have to cool off all the gases in the overhead and get it to condense back into liquids. That includes whatever water's present. And then if you have HCl gas with water, bingo, hydrochloric acid.
Yeah.
Yes, so corrosion is a big problem, and we like to get the salts out so we don't have that. I was going to say that the old refineries, the very first refineries, they were just a crude tower. Mm-hmm. Or actually, they were simpler than that. They were a pot, basically, that they built a fire under, and you distill off, the lightest stuff, and you condense it, and you sell it.
But then eventually they were going, hey, Frank, why is this thing corroding so fast?
I suspect, that eventually would catch your attention. But
and then they realized, wait a second, that salt is turning into hydrochloric acid and corroding our tower.
Right.
Not good. Let's get rid of the salt. Wow.
I was going to say that the simple refineries were just a crude unit. So you're running a refinery, you're making products just by boiling it in a distillation tower and condensing the diesel and the jet fuel and the gasoline and selling it. And the government's not bothering you about the sulfur, and so you just sell it, and you don't really care about the acid rain. Mm-hmm. Right? You're making big money off of this stuff.
Yeah, that's until people in the Adirondacks ask that, can we
all of a sudden, it's like, why are these trees dying?
The trees and the lakes, rivers of fish and all that wildlife. It's pretty severe.
So as it wouldn't surprise anyone, I think, to hear that the people that are putting their capital out to build these crude units and process this oil probably aren't going to put in additional millions and millions of dollars into additional treating unless they were essentially forced to do so. Mm. I'm speculating. There may be some history where somebody actually cleaned this stuff up there on their own good conscience. But in general, I think the regulations, one would have to say, forced the refiners to put in more equipment to be able to sell cleaner and cleaner fuel. I think that's a fairly safe thing to say. And indeed, if you're a refiner and you're trying to decide where to spend your money, because you have investments you want to make to make you the most money, because that's what the oil companies are in the business of.
Yeah.
They're going to want to know what's it look like for governmental regulations coming down the road, because I'm going to have to prepare whether I have to build another unit to take sulfur out or something to take nitrogen out, or what am I going to have to do next, and take that into account when you think about your 5-year and 10-year spending plan.
Because you can't build something like that overnight.
No, years and years.
So government regulations from the industry point of view are fine. Okay, we understand why we need to do this, but please give us some heads up and don't change them so quickly on us.
Yeah, and I'm not in that part of the business, but I can just imagine that you've got the classic lobbyists trying to help influence the government decisions, but I don't know how we got on this, but I think you were asking about why do we clean up sulfur? Yeah. And it's like, I don't think anybody did it just because of their nice guys. I think they did it because they were probably forced. But in any case, it is hugely shaped the refining industry over the last 50 years. If you look at how refineries used to be, they had a lot less different processes.
So
we have just started on the first process of a refinery, and there's a few other key processes, but some of those are mainly about taking sulfur out.
So post-fractional distillation, you have products still with the sulfur in it. Mm-hmm. And so you have maybe one pipe for gasoline, another pipe for jet fuel, diesel. And then you'll have subsequent steps to remove sulfur, as much sulfur as you need to, from each of those products.
Yes, and diesel's a super easy, good example, because it wasn't that many years ago. You could take diesel right off a crude tower, side draw, cool it down, and sell it. It had low enough sulfur, if it were low enough sulfur. There were still sulfur regulations, but they were looser, and you didn't have to do any additional treating. And that always kind of surprised me, all the different processes in the refinery to make the gasoline and on-spec jet fuel. But diesel, you could just pipe it out. That changed. Sulfur regulations have gotten tighter and tighter, and now you have to basically have what we call a hydrotreater. And what that is a process where you take the diesel, heat it up, put it at a very high pressure, and mix it with a bunch of hydrogen. So now you've got this gaseous liquid mixture, heated, high pressure, and you send it over catalyst. And in that process, basically, the hydrogen gets into the hydrocarbon molecule, which contains the sulfur, and it reacts the sulfur out of the hydrocarbon, and it forms acid? H2S.
Oh, hydrogen sulfide.
Hydrogen sulfide.
PU.
So, yes, that is one of the big dangerous components, if not the most dangerous component that we deal with in refining. And as you can imagine, it's very prevalent. it's almost
that's
everywhere.
That's why it smells when you get close to a refinery?
Especially in the old days. Nowadays, you really can't have much of any odors at all off a refinery. If you're smelling something off a refinery now, it's probably residual something that was left around on the ground years ago, or I don't know. But you're not supposed to be having any real odors off of refineries. In a well-run refinery, you can't smell. It doesn't have a smell. But H2S is the prime waste product, if you will, out of a hydrotreater.
Yeah.
And the diesel is clean. And now it's ready to go. So diesel is the easiest process, easiest fuel to make.
Aside from removing the sulfur.
Yeah, you pretty much sell it. Whereas gasoline, you have to do additional processing to make it high enough octane to not have to use lead, for example.
Right.
So you have to do other things.
So
is that why lead was used? Was it to increase the octane?
Absolutely, yes.
Oh.
That's the only reason why you had the lead additive, was to increase octane, which has to do with knocking of the engine. So if you don't have a high enough octane, the gasoline doesn't burn as well in your engine pistons.
The gasoline is C8, C10-ish.
C10's a little heavy, but there's C4s in gasoline. There's some butane in gasoline. Actually blend butane into gasoline.
And when we say like C4, C8, we're talking about the number of carbon atoms per molecule.
Exactly,
right?
Yes.
Where's diesel?
That's more up in the C10s, C11s. It's funny too, because that's the one thing when I came first to refining, I was used to, like in school, you're talking about specific molecules, and I know we're surrounded by hydrocarbon molecules in a refinery, but you very often talk about specific molecules. So something like diesel, you never talk about, well, what is it, a C10 or is it
a decane?
It's a boiling range.
Oh.
So literally
that which boils at between this and this.
Exactly.
It happens to be C10 to C11, but who cares? It comes out at this height on the fractional distiller.
Yes. And I mean, you can imagine when you're just talking C4s, C5s, there's only a few ways to rearrange those carbon molecules.
Yeah.
So a few different type of specific molecule names that you could go look up in the chemistry books.
Pentane, isopentane, neopentane.
Yes, there's only a few ways, right? You start getting up into C5, C6s, C7, C10s. Just think of all the different ways that you could arrange those 10 carbon.
Yeah, we talked about that in chapter 12 when we talk about configurations.
Right. So in the refining industry, you pretty much don't concern yourself too much with those various different ways.
It's boiling point.
It's boiling point because, that's what really defines how the fuel behaves when you're sending it out as a fuel for processing or for the diesel engine to use.
So crude oil comes in from different parts of the universe here on our planet. And the first step is to remove that salt. And the salt comes out, and then you send it. It's just getting warmer and warmer. You send it to the fractional distiller, and you heat it up, and the lighter molecules rise to the top, and the heavier ones don't rise so high. And based upon their boiling points, they'll condense at different altitudes, right, within the within the tower. And then so you're drawing off from that tower different products. At the top you'll have natural gas, and then below that maybe gasoline.
At the top you have natural gas, LPG, which would be propane and butane. So ethane and methane always stay a gas. Propane and butane mix between the gas and the liquid, because once it comes off the top, it is all vapor, but you cool and condense it because it contains gasoline. So your gasoline is all pretty much going over the top generally, over the top of the tower. And so what you get up there is a mixture of gasoline, propane, butane, ethane, methane, hydrogen sulfide.
In the methane, those more volatile compounds will just come out naturally.
The methane and ethane won't condense, because what I was going to say is you take that hot vapor coming off the top of the tower, you condense it. You put it through condensers, and you end up with this drum where after the condensers you drain this liquid vapor mix coming out of the condensers, and that liquid, you actually send some of it right back into the top of the tower, and it is what condenses the jet and the diesel further down. So you basically need, distillation will not work unless you have liquid against vapor. And so the liquid, you have to send everything up and condense it and to get a liquid going down the tower. And that's, over the top is gasoline. That's why you can condense it. Some of the butane condenses with the gasoline. Some of it stays in the vapor and goes out. But there's a gas pipe off of that drum we're talking about. And that will contain ethane, methane, propane, some butane, hydrochloric acid.
Plumbing.
Yes, the plumbing. Yes, we've got some part of the glorified plumber. But that goes back into the tower, creates liquid that's necessary for distillation. Then you can draw off jet, diesel, and heavier. And it's the heavier where now we have to do a lot more processing.
You had mentioned something earlier about energy efficiency in terms of something that the consumer society in general has to pay much more attention to. Could you talk about that a little bit more?
In refining? The energy efficiency in refining is all about making the most amount of money.
Well, within the industry, it's about optimizing every little detail as much as you can to make the most amount of money.
Because it's such large scale that every little bit makes
it
substantial
adds up.
Amount of money. Yeah.
But for society in terms of our energy usage, we're so dependent upon the fossil fuels right now, and there are a number of issues that come with using fossil fuels. One, peak oil, maybe we can talk about that a bit, but two, climate change, we could talk about that a bit too, I suppose. But you had pointed out the value in terms of society about their energy efficiencies.
Yeah, I was struck. I think I told you I was at an airport and it was early morning and I watched all these vans from hotels, totally empty vans going back and
like
forth.
Shuttles?
Shuttles, yes, hotel shuttles to the airport, completely empty. Back and forth, back and forth,
With
back
the
and forth.
driver in there just
the driver was just back and forth driving this.
But no one was in the
But nobody
van.
was in there. But because of our love of convenience, and if I stayed at that hotel, I'd want a shuttle. My whole feeling is, we've gotten pretty soft and used to the comfortable life, and we're probably being not as efficient as we could be. And that was just one of those easy examples, because it's not costing us directly any money for those shuttles to run back and forth.
Mm-hmm.
Now, if you stay at that hotel, hidden in your hotel charge, you've got a little money paying for the shuttle. But those hotels basically realize, if I don't have a shuttle, people aren't going to stay at my hotel. So everybody's got their own shuttle, and everybody's driving shuttles back and forth. And there's 7 or 8 shuttles waiting at a stoplight to pull into the airport main entrance, and they don't have anybody in them. And
that's just one airport.
That's just
it's
one
just
airport.
all over the world.
And that's only one few minutes of a day that I happen to witness it.
What a perspective you must have in terms of, there you are in your daily work, optimizing things as much as possible down to the finest detail to make sure everything is efficient and optimized, and then you're looking at that shuttle.
And I realize, yes, there's a fair amount of the fuel that we're making that is really maybe not going to be used in the most wise manner. And that would include each of us, right? Getting in the car to run down to the store for a cup of sugar. But we could have walked, maybe, right? Maybe it was a half-mile walk. Okay, that takes a while, but still. No, but it's so much easier, and I'll be the first to admit I've done it. I've got a half mile to go to the store, or I could take a half hour to do that. Oh, I'm going to get in the car. It'll take me 3 minutes. I'm not sure the people in the future will have that luxury. We've got that luxury, but I'm not sure that it's not a false luxury, just because we've been able to get so good at finding oil, refining it, competing to market it at the lowest price, that it's
squeezing out that last
right.
drop.
I guess it may not have all the costs of the future embedded in the cost of the fuel, is the right way of saying it. It's very hard to embed all the costs of the future because we don't have a crystal ball. So it doesn't get embedded. And how would it get embedded? In my opinion, I mean, just like the sulfur, it would take a government regulation to tax. We're going to tax this so that the future generations have a little bit more left. But,
it's not a bad idea.
Oh no! I mean, I don't know that it's going to happen otherwise. But that's just my opinion. I'm a glorified plumber, so.
Well, I'm interested in your opinion, in so where do you see energy going and our resources coming from, coming down the road?
Well, you mentioned peak oil. If indeed we have hit it, then every year we're going to be unable to get as much oil out of the ground. That's kind of the theory of the peak. And so if the theory is out of our world population that, this is how much oil we're consuming this year, then the assumption is, well, we need it that much to live. And then the next year we have less. So either we have to make up that difference if we want to live with the same energy consumption as a planet, and that will have to come from the other resources, the solar.
Well, what do you see as somebody who has a mind that's constantly working on solving the problems and creating, optimal situations for given what you have, What do you see as some of our options?
Just you mean the wind, solar,
Yeah.
bio?
Do any of those make sense to you?
Oh,
Do they
well,
feel?
I think you have that. They're going to have to be. I don't.
What do you see as the most promising efficiency-wise?
I guess I'm not in that business, but I have to feel like, boy, the more we could directly convert solar, that feels the most of our best chance of success, right? Because wind, it feels free, but of course there's a whole bunch of mechanisms that have to go into capturing that wind energy, not to mention the turbines and all the environmental issues with
the
turbines.
Magnets.
With the magnets, yes.
Yeah.
And I just was reading about turbine blades. After a few years, the turbine blades have to get replaced. Well, it's not like that's really that easy to get rid of all the turbine blades. But in any case, there's a lot of hidden costs in some of that stuff. So I would love it if there was some really, really super efficient way to just get the energy directly from the sun into our transmission lines. But I'm not into that business. But I would think that would be, if I were to bet on some of the future technologies that are yet to been discovered that may have the best hope for us, it would be solar related, direct solar.
Your colleagues that you work with in the fossil fuel industry, what kind of attitudes do you find from them relative to other energy sources besides fossil fuels?
Oh, we're the people I work with. We're all pretty much refinery nerds, and so we pretty much just are nerding out about making refinery more efficient or make more cleaner fuel, more efficient fuel, solving problems. But we don't talk about, at least I don't talk about, that's almost like bringing up politics or church. It's
just because you're all so focused on the job. You're engineers, and this is what we're doing. We're trying to get from point A to point B.
And plus, it would only be our opinions. But I've definitely worked places where I've heard some workers be very outspoken about the fact that there is no climate change. But as I said before, I think you've got a bell-shaped curve in any group in society where there's a whole side of that curve that are climate change deniers and a whole other side that are, very the opposite of that. So I would suspect that's the same in any refining area. Although I have to say, given that it's our business, probably some people are going to want to be a little more in denial about what seems to me an obvious thing, that the fossil fuels are largely a problem. One of the reasons why we've
the carbon dioxide.
The carbon dioxide, yes,
came from somewhere.
Yes, the changes in our atmosphere are pretty hard to deny, and it just seems so easy to explain it. I'm a big believer in Occam's razor, right?
The easiest way to explain it.
The simplest explanation, or the one that needs the least amount of complicating factors added to it, is a good one. It's like, well, gee, we had all these carbon atoms that got put in the ground millions and millions of years ago, stowed away by previous life forms.
Yeah.
And now in a few generations, what was sitting there for millions and millions and millions of years and took millions of years to form, we're going to take them out in a few generations and just put them all back up in the air.
With no impact whatsoever.
That would seem like a pretty easy explanation for where did all this carbon come from in the air? Where did this suddenly appear? Now, I know there's a lot of other sources of carbon in the air, and cows,
right?
But and other things. I'm just bringing that up as an example. But yeah, I think we played a pretty big role there. And I know there's got to be a lot of smart people that I work with that feel the same way.
Mm.
Good. I was thinking, we were talking the other day too about the role of efficiency, and that if we are going to have a energy issue or shortage in any way, then efficiency is going to be very important and key into using our energy well. And like your example of the hotel vans, shuttles. But we also got to talk about automation and how that's going to be an important factor to keep things efficient. That was interesting because we were also talking about what is society's role or humanity's role then if we just start automating things that need to happen in everyday life. Then
that shuttle will be a self-driving shuttle that'll only leave when a customer comes up to ask for it.
Yes, that shuttle will be so darned efficient. If you were to compare it to a human trying to be as efficient as possible, yeah, I think you have a lot of different things going into that shuttle's decision, that AI or whatever it is, the automation, I shouldn't say AI. The automation piece would have all these inputs, and it would already optimize, how to go pick up the passengers the most efficiently, and the light system, I think the stop lights and everything will all be tuned in and know where all the cars are and know where it's most efficient to make you stop. So it won't make a whole line of shuttles stop at 6 a.m. and sit there and idle for a minute at a red light when there were no cars within a mile in any direction. But anyway, I think automation.
Yeah, that's interesting.
I think automation can play a big role in helping us. And if we can get a solar energy that keeps us on our energy consumption path, I visualize this curve of our total energy consumption as a planet, and most of it's filled up by oil. You look at all the sources under that curve, and most of it's presently made up by oil. And if that oil curve starts dropping off because of the peak, then, like I said, you've got to now fill that area under the curve with some other source of energy, or make the total energy curve drop.
Right.
And
for society to...
And by the way, if we don't have a way to fill up the area under the curve with any other technology, like that great answer has not come, energy consumption will drop. Because there's no other hope.
It's not there.
It doesn't stay up at its present use just because we want it to.
Yeah.
So we don't. That's the whole idea behind the peak concept. Is like, gee, I'm trying my mightiest to get as much oil out every year, and I just can't. It's not there. I'm not getting it out. So once that's dropping off, and if we haven't made up that gap with other technologies, it'll drop off. So I'm assuming it will drop off, that we'll have to get more efficient because the oil piece of the energy curve is so huge.
Yeah.
Not sure we're ready for the other pieces just yet. Yeah.
What about exploring for more oil? In your opinion?
Oh, like say a beautiful natural area where we find a whole bunch of oil?
Yeah. There are ethical questions here now, aren't there? Should we allow the drilling there, or should we kind of force ourselves discipline ourselves into efficiency via the regulations?
Oh yeah, the shoulds. That's all very interesting, and it's so true. We should, right? We should.
But will we?
And so that's where it's like, I'd put it this way: I imagine a world where we haven't got that other technologies filling up the energy curve that we've left empty.
Yeah.
So as the oil energy dropped off, and the other curve
is it pacifying?
Wasn't big enough, so the whole energy is dropping off. So now all of a sudden, what's that do to all of our lifestyles? It's like, okay, when gasoline starts going to $4, $5, $10 a gallon, $20 a gallon, because it's just dropping off, and it's like, well, that'll force a lot of us to be more efficient to start with. But what do you think the society's outcry in general will be? But it's like, yeah, and there's a whole bunch of oil that would keep us at $3 a gallon, but it's kind of under some beautiful lands, and
but you never go there.
But still, it's like, we know people don't want to exploit those areas. So price of gas going up to $30 a gallon next week. I'm thinking they're gonna dig through that beautiful land. And I don't know much about that side of the business, but I do think that in general, there is an attempt to try to do things as how should I say, impact the landscape as little as possible. But you're still exploiting that area, and I just have a hard time seeing how we're going to avoid doing it.
It's like
unless we fill that energy curve.
We
got to have something else.
Tragedy of the commons.
I keep just visualizing. The curve I'm talking about, right?
Yeah.
So here's our total energy curve, and it drops off. and we've got to keep it like that. So that's all other energies.
Not only are you producing fuels, you're also producing feedstock for the chemical industry.
Very much so. Yep, some of those lighter molecules. Now, not all refineries do, but some refineries are really set up to make feedstocks for the chemical industry because there usually is more processing required. I've not been deep into that type of refinery, but they have to do some extra processing to make high-grade propylene, ethylene. Yeah, propylene, ethylene. These are all olefinic double bond carbons that are very easy to turn into polymers.
Right.
And those plastic bags, like I said, that you see in trees everywhere. So.
Okay.
So those are hydrocarbons with the multiple bonds are isolated from the mixture specifically for a refinery that's designed to provide feedstock for the chemical industry.
Yes. And actually, those molecules with multiple bonds, we don't like in our products at all.
They're reactive.
They're reactive.
Yeah,
so
they guck things up.
That's how if you put it in your tank with those double bonds, it would likely start polymerizing, and even in your tank, so that it gums up your fuel line and your fuel filter, and so
all that not good stuff, you just give it to the other people, the chemists, and they're going, that's good stuff.
Kind of, but actually the double bonds, as you know, are in all hydrocarbons. So if it's a C8, it might have several double bonds in its molecule, right? So there's double bonds in all sizes of hydrocarbon molecules, but we have to saturate them. So we make sure that you hydrogenate. That's one of the things when you go to a hydrotreater, it also saturates those double bonds. It not only knocks out sulfur, but it'll saturate.
You're adding hydrogen to those double bonds.
Yes, to saturate it, so it makes the fuel more stable.
Cool.
Yeah.
What would be the advantages or disadvantages of using another substance like corn or hemp?
I don't know much about the processing of how you make it, but I know you can get it. And I know the energy balance is not very clear when you take the whole energy balance of having to farm a field, which includes plowing and fertilizing and running your tractors. I've often used the example, if I put a huge double barbed wire fence around an area and gave some farmer the initial fuel for his tractor and the processing to be able to take the ethanol that he gets out of his field and future fuel his tractor and make fertilizer, right? Everything's got to come from inside that fence line. Make your fertilizer. I'll give you the plant to make your fertilizer, make your diesel for your tractor, everything. But your only fuel has to come from your field. I've often wondered how much ethanol leaves that fence line, or does he need more energy into the fence line?
He's actually putting in.
Right. So the whole overall balance of any biofuel is not always that clear.
So when it's not clear like that, you can argue one side or the other.
Exactly.
Well, there's hidden costs, as you were saying.
That's it.
Hidden.
It's not clear, and therefore you can argue either. And I think people do, and that's the lobbyists on each side are cherry picking and tilting the assumptions. Because if you were to try to, since we can't do that farm experiment with the double barbed wire fence, we have to make assumptions.
Yeah.
And those assumptions can vary widely, and you can make it look like ethanol is a huge payout, or you can make it look like it's not.
Even with photovoltaics, you've got to build the photovoltaics.
The what? Oh, the photovoltaics. Oh, well, there's an energy balance, obviously, on any thing.
So that's the wonder of the fossil fuels. It's coming out of the ground, and it's provided by nature.
There's a lot of energy to get it out of the ground and to distill it, and
very much so. That's an interesting point because, and as it's gotten harder and harder to get, you're using more and more energy to get it. So back in the old days, you remember the Beverly Hillbillies?
Yeah.
Jed Clampett goes hunting for something. He shoots a hill, and oil comes out. Well, those were easy days of getting oil out of the ground, and you may use 5 to 10% of your total crude oil. So it's like you get 10 barrels of crude oil and say, well, I'm going to set aside one of those, and that's going to be the cost of getting this other 9 to market. That was kind of like the old days. And now it'd be like, I better set aside 2 or 3 barrels for all the energy required to get these remaining 7 barrels to market. So that'd be a 70% energy return. And, of course, once it becomes barrel for barrel, right? As it gets harder and harder, eventually it becomes, oh, gee, half of my energy I had to spend just to get the other half.
So that's the reality of peak oil.
That's the reality of peak oil, exactly.
You would just have to be putting more and more energy to get less and less of a product.
Right, exactly.
Which means higher costs.
Pretty soon I'm spending 6 barrels just to get the last 4 to market.
I see,
now I've got to go 7 barrels to get the last 4 to market. And when it becomes, and that to get it to market includes getting it out of the ground, right? Yeah. Defining it, getting it out of the ground, getting it in the refinery, getting it processed, getting it out in the market. And if I had to use 6 of my barrels to get 4, and I'm selling it for $40 a barrel or gallon, I'm still doing it, right?
Yeah.
And then, but once I get to the point where, gee, I got 10 barrels out of the ground and I had to use all of them just to do it. It's like, you can't sell it for enough money.
So then I feel like we should talk about fracking too, because that has just
all of a sudden freed up a bunch of oil, right? Stuck in the ground. Right. I don't know that much about the process, but I imagine it's really hard to get it out of the ground. I'd have to spend all 10 barrels to get it.
Yeah.
But hey, if I just do some fracking,
blast into
whatever that
get
is.
it in between,
All of a sudden it's
that's primarily with lighter hydrocarbons, right? Methane they're pulling out from fracking.
I really am not a scientist around that, but I believe there is a lot of crude oil that has come out of fracking. So it's not just gases. So, and really that's why you do it. If you're an oil company, right? I like natural gas maybe, but there's plenty of that around, it seems like. I'm going to crack this earth so I can get the oil out.
Are there other ideas you'd want to bring up?
Well, I mean, we really only touched upon a couple of the bigger processes of refining, but there are some fascinating ones that have to do with rearranging the molecules, and those are really the fun ones. You take the gasoline, and it doesn't have good octane, but you send it into what's called a reformer, and you literally are reforming the molecules into
with a catalyst.
With a catalyst, and it actually turns them into some aromatics. It converts some of the C6s, C7s into
benzene
rings in a benzene containing ring, aromatic rings. Other things, branching of the hydrocarbons.
And that's good for octane. Right?
Very good for octane, right. So there's other processes where you're actually trying to get the octane up, and you're doing that by reforming the molecules or making molecules of branched quality. So I didn't mention, but there's a process where you're taking butylene, which is C4 butane, but with a double bond in it.
Right, trans or cis.
And you can mix it with isobutane and sulfuric acid, and it's called sulfuric acid alkylation. It's literally 99% sulfuric acid. We're talking essentially dry sulfuric acid. And it always amazes me that here's pure sulfuric acid. And I think it pretty does well. Fuming sulfuric acid, and it does okay in just mild steel pipes, right? There's other parts of the refinery where you have to use really exotic alloys and stainless steels, but just fuming sulfuric acid doesn't bother regular mild.
Don't stick your finger in it, though.
Well, that's the other thing. If you let too much water in, now that pipe disappears. Right.
So
just the fuming sulfuric, I always found it was interesting.
It needs to be aqueous sulfuric acid to
then it's very
really
acidic. Then it's very corrosive.
The water plays an important role.
Yeah. But that's one process that's interesting in refining, because you don't have to heat things up. It's really interesting. It's called alkylation, and you look in any organic chemistry textbook and they talk about alkylation. So that's one of the processes where we take light stuff like butane and butylene and actually make gasoline molecules. Put these butanes together and it makes a gasoline molecule that has a wonderful octane. So there's a whole bunch of the refinery processes around gasoline production, because, no surprise, here in America, gasoline is the big fuel. Maybe in Europe, diesel rules, but in America, gasoline rules.
Because you had mentioned the gasoline is only maybe 40% over there. And so with this reformation...
With other processes we haven't talked about yet, we make even more. So we didn't talk about there may be only 40 or 50% that you can boil off as gasoline, jet fuel, and diesel. The others, molecules are too heavy, and so we have to have other processes.
You can break them apart.
We can break them apart. Cracking. So cracking is a huge part of refining. You take molecules that are too big even for diesel, and you crack them, and they crack into pieces that you can use for gasoline directly or alkylation feedstocks.
So if the product's going to be gasoline, well, you can make it from non-gasoline molecules. The lighter molecules, you can join them together to form the C8, C9s. The C18 molecule, cut it in half, and there you have two gasoline molecules.
Yes, cut it in half. Crack it is what we call it. And cracking has been a huge part of the refining industry for past many decades. There's catalytic cracking and there's thermal cracking, where we basically, and that's actually one area, thermal cracking, you take asphalt, heat it up to 900 plus degrees, and it's so hot that it just kind of like shakes itself to pieces, cracks these huge, long asphalt type of molecules into smaller stuff that we can then process to make gasoline and
so
stuff.
Asphalt comes from
asphalt
petroleum.
So we didn't talk about crude oil structure is a whole range of hydrocarbon sizes, all the way from, like I said, the lightest, ethane, methane, all the way to super heavy molecules that are called asphaltenes, but they're just huge. They're some of the largest molecules kind of that exist naturally in nature.
Yeah.
And that's just in the blend. But you can't boil those. They boil at no temperature. So we heat them up and crack them.
So are you telling us that our roads are a big oil spill?
Our roads are indeed asphalts that
it comes from
that
the
from
refining
crude oil,
industry,
right? As a matter
oil.
of fact, some refineries, probably a lot of refineries, can't crack those heavy molecules. They don't have a thermal cracker process. So their only choice is, after they've boiled everything out they can get, and all they have left is this hot black. And when they cool it down, it actually is like hard, solid. The only thing they can do with that pretty much is either sell it as asphalt to make roads or coat roofs or driveways, or less and less nowadays, but they could sell it as fuel oil. So ships can actually burn that. And that regulation's tightening up as well, because that asphalt, by the way, is the
sulfur.
dirtiest, highest sulfur piece of the crude oil. And for years, recent years at least, the only place you could really burn that was in plants that had a lot of what you call tailpipe emissions control. So you're going to burn it, you're going to make a lot of SO2, but I've got the ability to scrub it out. Or put it on a ship and let them just burn away. And
out in the ocean.
Out in the ocean. So if you could you could just track probably this SO2 trail behind these big boats for years. And now it's tightening up a lot. So that's changing the refining. That's some recent regulation, actually, I think worldwide, that's changing refining economics as well, because you can't just sell that as easily for ships to burn. That needs some other work to be done to it, some processing.
Any other questions, Tracy?
Well, is it ridiculous to ask? I mean, would there be any reality to grabbing some of that asphalt and then actually restructuring or reforming those molecules for creating other fuel?
Cracking.
Oh, yeah.
Okay.
Absolutely. I used to joke about that, actually.
Like we'll tear up the old road.
After all the crude's gone,
we'll start taking the roads.
We'll start taking the roads up.
Okay. Yeah. And we'll have a different thing to put down.
I'm not sure that's realistic. I think the energy payout on that would be pretty bad. But
worse than the cornfield. I have two maybe ridiculous questions, but I have two questions. One is, what is the flame that you always see burning at a refinery? Why are you...
Well, there are emergency flares, and nowadays they really shouldn't be lit up all the time. And if you actually see a light up there, a little flame, it's what we'd call a pilot. So it's basically like the pilot in your hot water heater or in your stove. It's if you have a gas stove. But it's something there to ensure any fuel that does go up to the top of the flare in an emergency
will burn.
Actually burns.
Okay.
Otherwise, you're just spewing out unburnt fuel. That can lead to a dangerous situation.
Gotcha. Okay.
So there's pilots up there. But there are still flares around, but more and more they're trying to be... If you're seeing a flare nowadays, it's got to be very clean gas. It's got to be like probably just flaring excess hydrogen and methane, literally no sulfur. But the regulations are such now that anything you burn in a flare, other than in an emergency, has got to be as clean as the fuel that we're burning in our furnaces. So we have to burn pretty clean fuel in our furnaces too, like less than 100 ppm hydrogen sulfide, and generally we're down in way less than 100 ppm. Like we're in the 10 or 20 ppm hydrogen sulfide.
For that.
Yeah, but the flares are for emergency. So
Okay, got that.
when things go wrong.
Thanks. And then the second question is, as you're going through these processes, are there color changes? Like, does the crude oil come in one color?
Yeah.
And are these all different colors? Like that.
Yeah,
I
that's
just don't know what to
interesting.
picture in my mind.
Well, I know it's hard to say too, but if you just look at gasoline, it's light enough that it's generally kind of clear, even if it's just right off of the crude unit. Jet fuel, it may appear clear when you first pull it off the crude unit, but set it down in a bottle for a few minutes after it has been exposed to oxygen, and it will start changing colors, and so it will get more and more tan-like. So that's part of the stability. So try to get rid of those molecules that convert with oxygen and make color bodies. But yeah, diesel's always got a little tinge to it, perhaps, and then you get into heavier molecules, and they have some green colors. It's all pretty sludgy green colors. It's not real attractive, but and then once you get real heavy, then it's just black.
The asphalt.
Yeah, black. And that's what colors crude oil. If you look at crude oil, it generally looks black. So even though it may only be 10 or 20% of of it being asphalt or heavy stuff, it makes it all look black.
Rick, thank you so much for joining us here at the Big Picture Podcast. It's a pleasure having you here.
It's been my pleasure.
Yeah.
Thank you, John and Tracy.
Thank you. Learning so much. Thank you.